we're given a rod with total mass capital M and total length capital L. It's being rotated about one of its ends, so it rotates something like this. We want to calculate the moment of inertia, and we will be driving towards the parallel axis theorem with this exercise. So the moment of inertia, the general equation for moment of inertia is the integral of r squared dm, where dm is equal to lambda times dr, right? But lambda is just the mass density, right? The mass per unit length of the rod, which is capital M over L. So this is equal to capital M over L dr, like so. Okay, so then we could say that this is equal to, and notice that this is r squared dm, so we're taking each of these little bitty pieces of the rod and multiplying them times r squared and then summing them up. Okay, so then this is equal to the integral, and we're integrating from 0, from an r of 0 out to L. So from 0 to L, r squared dm, but dm is equal to this stuff, m over L times dr, m over L times dr, like this. So let's factor out the m over L, and then we have the integral of r squared dr evaluated from 0 to L. So the integral of r squared dr is r cubed over 3, evaluated from 0 to L, like so. Okay, so this is just m over L, and then this thing evaluated is just L cubed over 3. So let's bring the constant out front because that's traditional. Traditional to write it in that way. 1/3 times the mass, and then this cancels with one of these. This becomes a 2. 1/3 m L squared. That's typical because the units are kilogram meter squared. So you see you have a mass here. Excuse me. Typically you have a constant here. You have a mass here of kilograms, and then this is of course the length in meters. So kilogram meter squared. That's the units for moment of inertia, and so you know that we're on the right track. In fact, we are correct for this part of the problem. Now let's consider that this is equal to the moment of inertia about the center of mass of the rod plus some constant that we don't know. So we remember the moment of inertia about the center of mass of the rod. Well, this is a uniform homogeneous rod. Okay, and so the center of mass is right in the middle. It's kind of like this marker here. The center mass is going to be approximately right in the middle of it. And for this one, it's going to be exactly, because this is a theoretical construct. And so we remember that we calculated this before with L over 2 on each side. We calculated that I center of mass was equal to 1/12 ml squared, right? So then we have 1/3 ml squared is equal to 1/12 ml squared plus c. So then let's solve for c. C is equal to 1/3 ml squared minus 1/12 ml squared. Okay, so then this is equal to, all right, 1/3, least common denominator is 12. So 1/3 is 4/12. 4/12 minus 1/12 is 3/12. 3/12 is 1/3. So we have that this quantity, no, that's not correct. 12, right? 4 on the top, 4 on 12 minus, it's 3 over 12, which is 1/4, right? Okay, 1/4 ml squared is the difference between these two, okay? Okay, so let's rewrite this in a little bit different way. So I'm just going to come out this way. Let's first write this, let's rearrange things. This is m times L squared over 4, right? I haven't changed anything. Now I'm going to rewrite L squared over 4, this quantity here, like the following. That's true, isn't it? Right? That this, just square everything inside, L squared over 2 squared, which is 4, L squared over 4. So this is the same as this. Well, notice what this L over 2 is. That's the distance from the center of mass to the axis of concern, right? So we'll call that D. And that's the axis that we calculated explicitly for the moment of inertia, right? Explicitly. This is not the I center of mass, it's the I about some other place, right? The end of the rod in this case. Okay, so then let's rewrite this right here. So then let's write this as I is equal to I center mass plus C. So I is equal to the I center mass plus C, but we found C to be m L over 2 times L over 2 squared. But we noticed that that's just the distance from the center of mass to the axis of concern. And the axis of concern in this case was the end of the rod. So let's just write md squared. Right? Because this, and here's D. Okay, so this is the infamous parallel axis theorem. Notice what it says. It says that the moment of inertia about any parallel axis is equal to the moment of inertia about the center of mass plus the mass of that object times the distance from the axis about the center of mass to some other parallel axis. And it could be any other parallel axis. This is not a rigorous proof, of course. You can look at your book for that, but this is just a demonstration of it. Right? So let's say we have a rod like this. Okay? We know this. We know I center of mass. What's I center of mass? 1/12 ml squared, right? Okay, so we know this. And let's say we want to find the moment of inertia about right here. And that this little chunk right here is 1/4. And let's do, that would not be 1/4. I want to make this, at least to scale. So this is 1/4 L. If that's 1/4 L, then that means that 1/4 L, 1/2 minus 1/4, 1/2, I think it's 1/4 again. Yeah. Yeah, because 1/4 plus 1/4 is 1/2. And this is L over 2, and this is L over 2, right? Okay, so what this says is that if we want to find the moment of inertia about this axis right here, okay, which is, this is a completely different situation from anything that we've worked before. We don't have to do any integration or anything because we know I center of mass. So this is equal to, let's see how we're doing. Yeah, I got a little bit of space down here. 1/12 ml squared plus m times d, the distance from the center of mass axis to the axis of concern is d. And this is 1/4 L. Right? And it looks like a 4. Okay, so then this is L over 4. Okay, so 1/12 ml squared plus, okay, so L over 4, it's 1/16, right? 1/16 ml squared. Now I'm just going to add this 1 divided by 12 plus 1 divided by 16. 7 over 48. Okay? So about this, bizarre axis, at 1/4 L away from the end, right, is equal to 7 over 48 times ml squared. Now you could integrate, and you could, integrate from here to 3/4, I would be equal to the integral from 0 to 3/4 L, right? Because this is 1/4 L, the rest of it is 3/4, right? So you could, okay, r squared dm with all the usual substitutions, plus the integral of from 0, you have to add this, add up all these little pieces, right? From 0 to 1/4 L. If you want to do that as an exercise, you're welcome to, and you will see that you will arrive at 7/48 times NL squared. Okay, this is a quick demonstration of the parallel axis theorem. It's very useful. You will most likely be tested on it. You won't be asked to, do something like this. Probably not, I would say. But you will be asked to, be able to apply it and use it. And we'll work some examples along those lines. See you next time.